Right. So right now we're discussing basically the problem number D2, global round 16. So we just discussed the problem number D1 for all those people who don't have an idea how to solve problem number D1. We have already covered this. The video will be coming in the I button. I highly recommend you to first see how D1 will be solved because D2 is not that tough only if you have understood like how D1 has to be solved, right? So first go and watch D1 and then we'll come back to like how we have to solve D2, right? So D2 is just saying that there's one more additional condition that in D1 we're talking about one row, in D2 basically we have n number of rows and n is ranging from 1 to a particular value like 300 and we have to determine like what is the minimum possible inconvenience that can be caused, right? So we discussed like there were three steps to solve like the D1 problem, right? The step number one was sort it, right? Sort it either using array or the vector thing that I taught you like in the last video. Sort it. Step two will be right. Step two is simple, like for all those cases where ai is equal to aj, basically you need to make sure that si, if is less than sj, then I should be greater than j, right? So if for people who've done the sorting using comparator, you don't need to do it in individual steps, right? This it is only one step. But for people who have done a normal sorting technique, then you have to do it in a step two also to make sure that it can be done, right? So if you do it now, the step number three is pretty simple that you have to use BIT. Again, there are a lot of ways you can do it, but I use binary index tree, which is very easy. You can use BIT just to calculate like whenever a person is sitting like is going to set a particular position, then how many people were present before that, right? You can easily get to know that using BIT in a login operation, and like that's it. Great. So there were three steps to solve a D1 problem. Now when D1 easy problem, right? Now when we switch to easy to hard, like what is the difference between both of them, right? So the sorting essentially remains the same. You don't need to change a lot of it. Now this is where basically step two, if you do it in using a normal sort rather than a comparator, it will help you a lot, right? What I mean to say is that you need to check that if I and j, this is true, but also if I and j belong to the same row. Because if they don't belong to the same row, then you basically don't have to do this condition, right? Because if they don't belong to the same row, it hardly matters, if you place what one guy before the other, like without knowing if I is greater than or less than j, because it does not matter if a person is sitting in this row, a person sitting in the next row. The inconvenience of this is independent to inconvenience of this. So if you are making sure that you need to rearrange this case, there's one condition that has to be like covered again, that I and j needs to belong to the same row, right? So what I mean to say is that in D1 we were quite satisfied that if ai is equal to aj, then you can do one condition for always that for a higher index, maybe if j is the higher index, then place j before I. Now you also have to check that this can only be done only and only if I divided by m is equal to j divided by m, right? Where m is basically the number of columns in one row. When we do that, we get to know the row of the ith element, and that should be equal to row of the jth element. If you can do this thing well, great. Then only we can rearrange it with this possible case, right? So what we have to do externally in step number two is pretty simple, that whenever we are doing this, so this is basically d is a division function that I have made to get the greatest integer of the division, right? Just want to look like how d works, then that's how you do it, right? Just to check that if there's a remainder, just add 1 to the subtraction value and then return that. So it's a greater number division, and just to check that if the row of this particular case is equal to this, I'm iterating over the total number of vertices where the eyesight value of people this is equal to the eyesight value before the person just before, and the row of these two guys are same, then only we can switch to the next possible person, and then we can just reverse it to the last position, the first position with the same eyesight, to basically the greatest position with the first eyesight belonging to the same row, just reverse them. to make sure that you have the best possible sorted seating arrangement, right? So you just go about understanding like how this works. Great. So it's simple. I hope you guys would have understood that we need to check this condition where the rows are same. Now, okay. Now, if we have just got to know the number, if the row of ith number is same equal to jth number. Now, there's one more change that we have to do, right? In the D1 problem, we just needed to calculate like if person is standing over here, how many people are there before him. Now, in this particular case, you need to do one more thing, that you have to first find the row, and then in that particular row you need to calculate number of people before them. Well, it can simply be done again. I used for this case normal BIT. Well, you can, in this case you can use a 2D BIT. 2D BIT. However, operation will be done only in one dimension, right? Operation has to be done in one dimension, not a traditional 2D BIT where you have to use operations in both dimensions. Like what I mean to say is that you can make a vector for binary tree where like this is a vector of n plus 4 I've kept for like just to balance out basically the we don't get to an extra index. That is not possible, right? You can do an n plus 1 also, it's not an issue. So we are basically storing n plus 1 binary index trees, right? That's how you can understand it. So for every row we have kept a binary index tree. We just simply go and again use this function to find like what is the particular row that we have. Then the position that particular row, we can do that by doing the remainder to get it. Well, you have to handle one more case, that if the remainder is 0, then basically the position is m. Position is not 0, right? Because we don't have a position 0 in the particular row. It has to be from 1 to m. And then we can just calculate it in that particular row using BIT, and how many people were before him, and update in that particular row, the row belonging to that particular binary tree with a plus 1 value, and we can just simply return with an answer value, right? So what I mean to say is that if you have a 2D BIT, which is nothing but n binary trees, right? N binary trees, then first find the row, right? First step, find the row, and in that particular row, like if tree row represent the binary tree of that row, find the answer, calculate the answer, and update the answer, right? So again, that's why I was saying that D2 is heavily dependent on D1 because it's like 75% essentially the same problem. What we have done is a couple of steps we have added. First, when you are rearranging, we are making sure if you are rearranging numbers after sorting, then do that only if one condition is added, that they need to belong to the same row. Secondly, calculation will now be done using n binary trees, right? And that is it. You've solved the problem, right? So the problem was quite an easy problem, but for that you just needed to understand how D1 is working. If you solved the D1 problem, D2 was quite an easy problem to tackle, right? So hopefully hopefully you just understood how to solve the problem. If there are still doubts, I'll still recommend just do go and watch D1. I think a lot of people would not have seen how I've implemented D1. Then you'll not be able to understand like how I've used a binary tree and why, rather than using basically a comparator function, I was just doing a sorting, and I was just getting like what are the total track of people who need to be reversed, right? Instead of using a comparator function to get the right seating arrangement, right? So just do watch a D1 problem. You'll get to know how it has to be solved. It was an easy problem, nice problem, and hopefully you'll get to understand like how you have to go about solving the problem, right? So till then, bye bye, see ya, have a very nice day, and meet you forward with the next question.